Hello, welcome to our second session on SPC. If you missed the first session, I put in the link to the first session's video on the chat, so you can watch that at your leisure. Today, we're going to be talking about the first charts, variables control charts. Our speaker is again Jim Bossert, who's a senior performance excellence consultant with John Peter Smith Hospital in Fort Worth. Prior to that, Jim was a Lean Six Sigma and Change Management Master Black Belt for High Reliability Initiatives at the Joint Commission Center for Transforming Healthcare. In this role, he was responsible for leading and coordinating activities supporting the adoption of high reliability practices with hospitals and state hospital associations. He has been actively involved in quality and process improvement in all levels of management for over 35 years. He has presented at numerous conferences as well as written papers and webinars to share with others his learnings. His experiences in a variety of industries have allowed him to help many diverse industries in the implementation of rapid process improvement. Some of these industries are automotive manufacturing design, chemical and process manufacturing, mobile phones, banking and finance, performance excellence consulting, software development, and teaching. Dr. Bossert is certified in green belts, black belts, and master black belts in these industries, and he was named Quality Magazine's Quality Professional of the Year in 2018. He is well-versed to give us this talk today, and I hope you all enjoy it. I'll turn it over to Jim.
Thanks, Jenny. Well, hello, everybody. We're going to have an interesting historical day today because we're going to talk a little bit about how did control charts ever begin, what was involved with them. So we're going to start first and talk about a guy named Walter Shewhart. And just as a point of reference, back in the 1920s is when Walter Shewhart started to think about how can I better control my processes? Because telephones back then were very bulky. They were expensive. Okay. People expected them to work almost like we do expect things to work today, even more so then. But also, rework was extremely costly. And part of that was because you had a lot of travel, you had materials, and you had time. There weren't that many telephone manufacturers back in the 1920s. And so as a result, if you had something that had to be repaired, they either had to send a repair person to your location or ship it back to the main location. And Western Electric was the main manufacturer. They were located in a little town called Chicago. Okay. And Walter Shewhart, who was a physicist, not an engineer, but a physicist, decided that, he was tasked with working on improving the manufacturing process that would reduce field repairs. So, that was some of the challenges. And, if you think about it, how long does it take a train to go from Chicago, we'll say, to New York, or Chicago to Houston, or Chicago to LA? That would be time that an engineer would have to go and sit in the train and wait. And, they didn't have cell phones, they didn't have computers, so it tended to be a difficult ride at best. Shewhart basically had an interesting theory. And his theory was that all processes have a natural state. And the natural state was stable and predictable. So he said that if I know when I have this state and it's predictable, and I can say that works most of the time, then that's what we're looking for. He also felt that, how does a process become unnatural? Well, something goes on to cause it to go wrong. Something from outside. Okay, so he was talking about, how do we minimize the impact of outside influences on a process? At the time, that was kind of a radical theory. Not many people really understood much about processes or doing stuff like that. So it was kind of interesting that he approached it. And so when he was putting it together, he said, well, I'm a physicist, so I put everything in mathematical terms. So his theory is that if I have a process mean and I look at things like central limit theorem and I look at all this kind of stuff, I can say that, the distribution of averages is always normally distributed. And I know that, if I take a distribution of individuals versus that of the averages, and you can see the dotted line there and how much wider it is, that may not be normal. And he felt like I need to assume an underlying distribution of normality. And he says, you also need to say, if it's going to use a mean and you're going to have a process mean or a grand mean, whatever you want to call it, then I need to think about, what does that mean in terms of what I expect to see in terms of variation. Okay, so he looked at something and he ended up calling them control limits or action limits, and they were plus or minus 3 standard deviations around the mean. But he took the standard deviation and he divided it by the subgroup that he was talking about. And we're going to talk about that because the first chart that he created actually had to do with what he called rational subgroups. And we'll get more about that in a minute. He also said, if I do that and I'm assuming a normal distribution, that means that 99.27% of the time, everything should be fine. But if I get something that's really critical, I might want to react sooner. So he developed also a concept of warning limits, which were 2 standard deviations. And if you remember correctly, 2 standard deviations addresses 95% of this stuff going on. So he wanted to have that kind of thing saying, if something hits over there, it may be something I want to look at and do something about. Okay, so that was some of the things that he had as his basic premise. Now, he wanted, though, this was his theory, and, he wanted to make it real by putting control limits in place, but he also had to figure out, was this even going to work? Now, back in the 20s, they didn't have anything known as a computer. They didn't even have calculators. Okay, so what Shewhart did was he borrowed one of his wife's mixing bowls and he got a bunch of poker chips. And on the poker chips, he labeled them 1, 2, 3, 4, 5, and then minus 1, 2, 3, 4, 5. And he started pulling out chips in a group of 5. And his logic improving in doing it with a group of 5 was, if I pull 2, I don't know if it's good or bad. If I do 3, then I see if one's good or one's bad. But he said, I can pull 5 things at a time and get a better feel for what's going on in terms of variation. Because I have where it's centered, and then I have 2 other points on either side to get an idea of, is it kind of skewed or is it straight? And he pulled those chips out. He totaled them up, calculated the average, and started plotting it on a graph to see what it looked like. So that's how it started. And for those of you who ever get a chance to go to Milwaukee and ASQ headquarters, they have Shewhart's wife's bowl as one of the things in the display case. So you can go see what it looks like. It's not very remarkable. It doesn't make you, it's not golden or anything like that, but it's kind of cool to see it. And Shewhart was a very practical person because, when he talks about quality and control charts, he took it from an economic perspective of quality is what he called it. So he focused on the economics, the business side. So he didn't want to have engineers to go out unless there was a rare event. And a rare event, he said, defined as something beyond 3 sigma limits. Okay, so that's the only time he would investigate anything. And if you think about it, that's kind of an interesting premise because he's saying, okay, this is going to happen 0.27% of the time. Okay, so he was trying to get an idea of what's going on. So, and he said, if the process is between the 3 sigma limits, I'm going to consider that common cause. and I'm going to call it in control. He kept it real simple in the beginning because people had no idea what the heck he was doing, why they were doing it, what was the driver. So, he wanted to make sure that it made sense and it was easy to understand. Now, if it was out of control, then he said special causes were doing it, and that is up to us to identify special causes. And as we go through this, I'm actually going to give you some examples of some different processes that have taken place where you can get an idea of how to look for special causes or what special causes might be. Now, when he asked people to look at it, back then they did root cause analysis, trying to figure out, what did it, but it wasn't as, I'll say, organized as it is now. And, with the Ishikawa 7 quality tools, we have things like the cause and effect diagrams or fishbone diagrams, SIPOC diagrams, SIPOC standing for supplier, input, process, output, and customer. So you're looking at each process step and saying, what's the result of that process step? Who's the customer for it? What's the input for that process step and who supplies it? And the 5 why analysis. These weren't around back then. Well, maybe the 5 whys was, but I don't think they thought of it as a formal quality tool. They just would ask why and try to figure it out. Okay. But anyhow, he wanted to take the theory to reality. So the first control chart Shewhart developed was just an average and range control chart, otherwise known as an XR chart. Okay. And it consisted, the basic element that made it unique was this thing called a rational subgroup. And, what is a rational subgroup? That's probably the key question here. Just like common sense. What is common sense? What may be common to me may not be common to you. So therefore, we have to define it. So we're going to talk a little bit more deeply around rational subgroups, but think of it as a grouping that makes sense for the analysis, whether it is a day, a week, an hour, a half hour. Okay, what made sense for the grouping? And the whole thing is that since we're looking at things in a group, we want to have a group that has very little variation within the numbers that we're looking for, but we want to have a look and maximize the variation between them. Okay, so we want to keep that in mind. So we start looking at XBAR in our charts. This is kind of what they would look like. Now in this one, we have a well-behaved chart. Look, it's all between the limits. Oh, isn't that nice? We see the variation going on and we're very happy with it. Just like we talked about in session 1, we talked about how do we handle variation. We're looking at variation over time. That's all we're doing here. Okay. Now it is continuous data. If you remember, continuous data is stuff we can measure, whether it is time, whether it is weight, dollars, whatever. But so we have here, and it happens to be processing time. Okay. And when we look for an analysis, everybody wants to jump to the XBAR chart. We're going to focus on the range chart, which is the lower one, the first one. The range chart is the chart that determines how wide the limits are in the XBAR chart. And this is what's important to us because the wider the limits are, we can better see what the process is, but that also says I have a lot of variation within a subgroup. So the first why I look at the range chart is I want to see, is it stable? Are they all between the limits? If they are, then we can say they're stable. If it's stable, then we know the limits for the mean chart is going to be also good to look at. Something else to think about here, though, with the limits is when we calculate limits, we have to be as consistent as possible. We're using the same subgroup size, so therefore they're straight lines. Some of the new control charts that have come out that you have in various statistical packages will allow you to have variant subgroup sizes, and it gets the choppy building effect. It's very distracting to look at, so you want to be careful with that. Anyhow, back to the XBAR chart. So we're looking now to see what are the changes in the average. are the changes just random variation going on, or is there something happening? In this case, looking at this, it is just random variation. So we should be very happy. Wouldn't have to touch anything or do anything. It's doing exactly what it should do. Okay, so that's the kind of thing that we're looking for. All right. Now, why is this important? Well, the X bar chart is, we're looking for changes in the mean. This is the most powerful chart you can use. And so we say it's the most sensitive for tracking changes around the mean, because we can tell differences very quickly and can react quickly to them. All right. Shewhart, though, and going through it, Western Electric's a big company. He got people to use the X bar on our chart, but they ran into some difficulty because they recognized that sometimes they got things that they can't take a subgroup for. So they needed to create another chart. So Shewhart put on his thinking hat, and he had a fellow statistician working with him by the name of W. Edwards Deming. And Deming basically kind of told Shewhart, we need to do this because I got processes where I have destructive testing. I'm destroying stuff. I can't take a subgroup size of 5. We're going to destroy too much material. It's not cost effective. Okay. But he also said, sometimes we got to just make a quick decision. Is it good or is it bad? But we're using numbers and not going pass fail type thing. So you have to look at it and say, what kind of process might you have? And those of you that work in the chemical industry or process industries, you may recognize continuous processing. You've got to make a decision quickly. So you can't always take a subgroup size of 5. Okay. If you're in the medical industry, people are not going to go and say, a doctor's not going to say, well, wait a minute, I have to get 3 more people here to get the same diagnosis before I can say we're right. It doesn't work that way. So you have to be able to do it. So, he started looking at things. One of the other things that came up out of the chemical industry, for example, is there's a shelf life in certain products. They only last so long. They're only good for so long, and then they degrade. So you have to do something. So they created a chart for individuals with a moving range. And the concept of a moving range was very intriguing to a lot of people, because that was something that they kind of looked at and go, what are you trying to do here? Well, what Shewhart wanted to do was create what they called pseudo subgroups or fake subgroups. And a moving range just takes a number of data points. And you're going to say, if I have a moving range of 4, like 4, like I have an example here, I'm going to start with 0.1 and go over 4 points. That's my first subgroup. But the second subgroup is not 5, 6, 7, and 8. It is rather 2, 3, 4, and 5. It's the next group. I'm just moving over 1 and just creating a range that moves with it. So it becomes almost, if you looked at it on a control chart, it might almost look like a snaky line because it's always moving just a little bit. And it's kind of neat because the moving range really is a powerful tool, can be used. And this is what one looks like. Now, this is process time. Okay. There's no subgroups. Okay, so each measurement represents one batch of product. In this case, it's a batch of chemicals. Okay, and the assumption here is that the production rate is slow, so we can have measurements at a wily space and time. So that's what's going on with this particular one. Now I'm gonna play a little joke on you this time. If you look at this chart, this is the same chart you saw on the means, but it was taking a subgroup size of 5. Now you see what it looks like with a subgroup size of 1 with a moving range of 4. Okay, think about it. This is a lot more variation. It shows looks a lot busier than the one we saw earlier. And that's an important concept. When it comes to looking at analysis of charts, sometimes you want to look and take a step back and look at things over a longer time period. so that you can better see the patterns in terms of what's going on. Okay, so this is just giving you an idea of what the individuals chart looks like. So we talked about individuals in moving range. We talked about X bar and R. There's another chart that's come that people like using. It's called the X bar and S. Okay, and the S stands for standard deviation. And this has become a lot more popular now that we can pull data from computers and get larger sample sizes or subgroup sizes. So as a result, the standard deviation chart is also very popular. The rule of thumb that we tend to use is that the subgroup size is greater than 10. All right, and what you can see is that when you have it, you can see the chart and it goes on. All it is looking at standard deviations. You're still looking at the S chart now, okay? And saying, is the measurement within the group, subgroup stable? And if it is, then it'll calculate the limits. It will give you a more precise estimate of variation. And that's because you've got a large subgroup size and standard deviation tends to be a little bit more, for lack of a better term, stable than the range chart. So as a result, your limits are going to be a little bit tighter around the mean, but they're also going to give you better estimates. Now, this is not a class in statistics. This is not a class in mathematics. I'm just showing you what the calculations are. If you have statistical software, you can see exactly how it works and what it is. Basically, what we're doing here is looking at, for a traditional chart, the grand average plus or minus 3 standard deviations divided by the square root of n, and the n is the subgroup size. When you talk about individuals, it's the grand average plus or minus 3 times the moving range. And the moving range grand average is what we use. So those are just some of the differences, and those are the calculations. It's not rocket science. This is fundamental blocking and tackling when it comes to statistics. But let's talk about a rational subgroup, because the challenge we have here is what is rational and what makes sense. To me, this is always one of the challenges we have when I'm trying to set up any kind of control chart is what should that subgroup be? How do I do it that allows me to see what is going on, but minimizes the variation? Okay. So if I look at this as an example, all right, I have a bunch of data here over time. What I've circled is various subgroups that I'm looking at. And what you've got is, if I look at the mean of all these, the means probably be very consistent. There'll be some variation, but they're going to be pretty stable. If I look at the range chart, I've got some subgroups there that I have wide dispersion in range from low to high. I have some that I have very little dispersion. So the range is going to be kind of different. Okay. Now, when I have large dispersions, I will have wider control limits. That may not be bad, depending on what the variation in the process is. So if you have it, you're going to look, and if I looked at this, I'd probably say I'm not going to have a lot of outside variation in terms of the mean chart, because the limit's going to be very wide, so it's probably going to look and say it's fairly stable. But if you look at it, are these equally spaced in time? Okay, and that's the challenge we have in terms of sampling and subgrouping. Okay, so what I want to do is let's go through a couple examples. I'm going to show you some different subgrouping, and we're going to talk about the strategies. The thing is that we have to think about what is the difference within the subgroups and how much is going on within a subgroup. But you also have to look at what's going on between it. Is there something going on there? And when I look at the process, is the range changing over time? Do I see something where the range is getting wider or it's getting smaller over time? It could be a sign of something wearing down. Okay, or it could be if I'm using some kind of screening mechanism, the screen is getting more full. So as a result, what's happening is less is going through, so the variation is shrinking. I also want to look at what the average is doing. Is the average changing over time? Is it getting bigger? Is it getting smaller? Toolware control charts frequently are used because why? You can see the mean change and you recognize you have to take the tool down and do some retooling. Okay? Or if you're doing some lab experiments, as your lab sample or as your golden sample degrades over time, you have to basically make some changes to it. So these are important to think about as we build it. So here's one process. Now this is kind of interesting. If you look at it, we have what I call a snaky line. Depending on where I look at this, the range within each subgroup really is not changing much. So it doesn't matter where I pull it in terms of the within group variation. What does make a difference is where I pull it, where I pull the samples in terms of time. If I pull it where they're peaking or at that bottom, I get a totally different picture of where the mean is and how the process is running. Then if I pull it over a period of time, that shows lows and highs in it. So, it's important to understand what the process is doing. And if you remember from the session we did a couple weeks ago, we talked about understanding variation. This is why you want to plot data over time so you can see what's going on. So if you have to make a control chart where you're going to do some rational subgrouping, you got an idea of how frequently you've got to pull these. Okay. Now here's another one. This is, again, you see fairly stable process, except for a couple of times where you see what I call the bubble appear. And if I if I take my subgroups before the bubble and after the bubble, I don't recognize I may have increased variation for a short period of time. And if the customer sees it, it may not be acceptable to them. So we have to, again, think about how do I pull it? The other question I would have is what's causing that bubble? Is there something going on in the process that I need to recognize what causes that to occur? Is it something I can do something about to make it more, so it's more like the parts in between, which are very stable? Okay, so we have to look about that and think those are doing. In this one, we have a very interesting process that if it was all grouped together in an X bar is in a XY plot, it would look like a big shotgun pattern. Notice as we pull it in time, we have sometimes where the grouping is very high, other times the grouping is low. A lot of variation seen here. And it would be, we have to think about how we would pull the sample. How many samples, how many numbers in the subgroup might I pull? Just to get a good idea of the variations going on here. So again, think about what's happening with your process and how you pull the samples. And then finally, we have this kind of grouping. Now, this is a grouping that's typical of something that's tool wear or degradation over time. So what we're seeing is the variation is increasing over time. So if I'm pulling a sample here, I want to be able to make sure it's consistent, but I can catch it so that when it starts getting too big, I can react before it gets out of control, or even worse, out of the acceptable specification that the customer is asking for. Now, notice I didn't mention specification till just now, and that's simply because I didn't want to. Specifications have no meaning in a control chart. We look at the control limits and we look to see how the control limits work and what they're doing with it. So we're looking at that variation and saying, how do we make it work for us? Regardless of what it is, whenever I'm looking at a subgroup, and I'm spending a lot of time on subgroups because it's very important, what has changed within the subgroup? If the process is showing me out of control, What changed? What's going on there? I also have to look at the counter of it. What didn't change? And those kind of sound like they're counterintuitive, but they actually work well together, because if you know what changed, that's fine. But if you're stumped and you ask what didn't change, now you start adding all the common things that you got and saying, okay, these are the stable ones. So what caused that variation to start changing? The same thing with the mean. When we start looking at the means, what changed between subgroups? What was going on versus what did not change? And I think, that's something that, again, these are the 4 fundamental questions you ask with any control chart. And it gives you a sense of what's going on, what you're doing. Let me give you, I've got a bunch of examples I'm going to go through and just give you a sense of, what's happening and what isn't. We want to track how long it takes to process a person who walks into emergency before they're actually being taken in for some kind of triage. Okay. We're going to look at 5 patients for each hour. So I have the first subgroup. And this is the times I've got. Then I took the second subgroup. Notice the times are a little bit different. Again, still going on, but I'm trying to take, said an hour is the subgroup interval I'm interested in. So as long as I take 5 times in each hour, it meets that time frame. Ideally, I want to change it so I'm not always taking it at the exact same time, because there may be something going on that takes place at a regular interval that I might inadvertently get. So that's why you want to look at it and take your times and look. Okay, so we've got those. If you look, here's what the X bar chart looks like. Here's the X bar is 30.67 minutes. So we're saying it's 31 minutes on average you're going to wait before you're seen by a doctor. Is that good? Is it bad? It depends on your experience. I mean, and there's other factors going on, but fundamentally, it could take a lot less. It could take a lot more. It just depends on what's wrong, what day of the week it is, what time it is, what's going on, what time of the year. Okay. Jenny and I were talking before. She had 37 degrees this morning up in Minnesota. Okay. I'm down here in Texas and it was a lot warmer than that. But think about wintertime. Accidents occur more in wintertime than they do in the summertime. Why? There's snow and ice. Okay, especially the first time you get snow and ice, you get a lot more accidents. A lot more accidents means a lot more people might be going to emergency. So it might take longer, okay, because you had your first snow or first frost. Okay. So it just depends. But if it took me 31 minutes, I'd probably be pretty content with that. This is a pretty stable chart. We have only we got one data point there. It looks like it at subgroup 27. It's real low. Okay, we might want to look and see what that is. It might be it's that patient was real quick because maybe it was a patient that was bleeding. Okay, person comes in with bleeding or a heart attack, they're going to be seen right away. They're going to rush them right back in triage and do something. They're going to stop the bleeding. They're going to check to see if they're having a heart attack. So certain things trigger emergency crews to work. Okay, and work faster. Okay. Here's the range chart. Range chart doesn't show much variation at all. It looks really kind of pretty stable. Okay, so it's kind of cool. Okay, look at that and go, wow. That's pretty stable for considering we're taking 5 readings every hour. Okay. Like I said, on average, there's a 31-minute wait. Okay. Could be longer, could be shorter. Biggest range that we have there, 42 minutes is the longest one. So we do have some extreme times there. But you got to think about what it is. We talk a little bit about what can cause that. Now, let's go to pharmacies. Nobody likes going to pharmacies to get medication because you never know how long it's going to take. In this case, I'm looking at what's known as a specialty pharmacy. And specialty pharmacies are looking at formulations for chemotherapy. So they're looking at special formulations they're making that are chemical in nature, they're liquid. Okay. And basically, they have a shelf life. So they can't sit on the shelf very long. They have to be made up within a certain time frame and given. All right. So this is going to be something that lends itself to an individual moving range chart. And if we look at this, there's the average time right here. Okay. And over a month, it's looking at it and saying, wow, I got a average turnaround time of 102 minutes. So less than 2 hours from the time it started to the time it's made. Notice though, when it starts here, when it first started in April 2023, it was over 2 hours. So they did reduce the amount of time it takes to make preparation of this chemical and process it and to give it to the patient to be given. Okay, so the process is a little more stable. Look at the range, and like I said, when the moving range, we see a huge decrease from the initial start to when we finally get down. So they're getting better in terms of the amount of time it takes to make it and deliver it. Okay. So 103 minutes. Time to process those moving so that it finally got down to an average of 14 minutes. So they can produce a product in less than 2 hours if they need to. That's a pretty important thing if you get chemotherapy. Because depending on how the product is being given to you in chemotherapy, it could be done in an hour, it could be done in 2 hours. But turnaround time is important, and freshness is very critical. Let's talk a little about warning limits. I mentioned them briefly in the beginning. Warning limits are there when you want to react to a problem sooner. Okay. Usually it is set at 2 standard deviations or 1.5 standard deviations. If I go with 2 standard deviations, what I've got is I'm going to have a 5% alpha risk. If I go 1.5 standard deviations, my alpha risk is a little bit smaller. Okay. A little bit bigger, I should say. So a lot of times what you tend to find is 2 standard warning limits are usually set at 2, plus or minus 2 standard deviations. So in this case, I've got a chemical manufacturer, okay, and they're mixing chemicals. And when they mix chemicals, you've got to be very careful. So they take samples on a regular basis, and they basically need to look at whenever the warning limit crosses the warning limit for their sample size, they have to add some more chemicals in to stabilize it. If they don't, they have a violent reaction. I say like an explosion, but that's why a lot of chemical manufacturing areas have what they call blowout walls. So if an explosion occurs, the walls blow out in their way to deflect the damage. Okay. Having worked at a chemical company and seen some of this take place, I got to really appreciate the value of warning limits. And I think it's something that we all tend to think about and want to take into account. In this case, though, this is a building manufacturer. And what they've got is they're making insulation for windows and doors. And the insulation is the foam stuff you see that goes around windows and doors. Okay, you want to basically use a chart that controls so you can decide if you have to speed up the line or slow it down, because the urethane gets put on and is a liquid. It is then sealed and forms into the shape that the seal is set. Challenge we have though is that we don't want it to expand too quickly so it bursts. Okay, so we have to monitor the temperature every 15 minutes. And so as the expansion goes through, we want to see this, and make sure that there's no problems, because obviously if the urethane breaks the plastic outside of it and the mold forms a different shape, it can't be used. So, using this kind of chart is very important. So if I look at the temperature, and these temperature tunnels tend to be very stable. Well, they form the shape that you want it to as you go through. So it's usually a bead of some kind, or maybe some kind of funny S shape. But you can see we want to have stable temperature as it goes through. So we're looking at it, it's pretty stable. Look at the range, though, we do see some fluctuations going on. So that's something that we have to remember, that the range is going to change. Range can be impacted for this stuff by outside forces such as humidity outside, temperature outside. If, for example, spring and fall for certain manufacturing processes are horrible because you have fluctuations in temperatures and humidity. And as a result, for processes that are sensitive to temperature and humidity, it creates a lot of havoc for them. They would rather have a constant temperature and humidity. It's cold or hot as long as it's constant, because that's easier to control. So you have to think about that as we go through and start building what some of the processes are and what's happening. The thing is, with this process, the temperature changes weren't extreme. They originally thought this was going to be more of an issue. Line speed changes, they didn't have to do as many as they thought. Okay, so as a result, they were better able to set up a process that was going to work, and basically tried to figure out, was there a better way they could do temperature measurements or do it in what they call temperature zones. Okay, give you some examples. Let me give you another example that actually I ran into this morning. So let me kind of set the theme for you. One of the things that in healthcare they worry about is people, they get into the hospital, they're an inpatient. People want to get out of bed sometime because either they have to go to the restroom, they just want to move because they've just been lying down, they can't stand it, so they want to get up. Thing is that when you've been lying for a period of time and all of a sudden you try to move, you're dizzy, you're a little bit unstable, and so falls can occur. And when you have a major hospital, in this case, the hospital has 10 different floors that they're looking on, some are what they call critical care, which are people that usually are just coming out of surgery, so they're watching them very closely. They have some that they call just intermediate care, which is people that have been in the hospital a longer period of time because of something traumatic that happened, and so they have a longer stay. So they're looking and saying, could they see a difference? What are the things they're trying to do? So we actually did some control charts on the different floors. Now, the challenge we have is that each floor holds a different amount of people. So what we had to do was we actually had to take the average census, or the average amount of people that are on any given floor, and we tracked the falls they had. So we actually normalized the data to the census and then took that ratio and we're plotting the ratio. And as we looked at it, it was a very interesting phenomenon because the person I was working with had a theory that certain floors were going to have more falls than others. But yet when I actually pulled the data up and looked at it, it was all the floors were within plus or minus 2 standard deviations of each other. And that was really interesting because now all of a sudden he looked at it and realized there isn't that much different from floor to floor. It's just, and the occurrences is the same. It's just that people always thought certain floors had more because they had a larger group of people in there, larger census, but proportionally, it was all the same. So these are some of the things that you wanted to have. Okay. So that was an example, and I came up, it happened this morning while I was doing some analysis. So it's kind of cool when you got something you can actually talk about and plot it. So, okay, with that, I am done with the formal lecture. So I'm going to open it up. If there's any questions, feel free to type them into the chat, and Jenny will read them off, and we'll see how we can do an answering. Did I put everybody asleep? It's after lunch.
So what's the hardest part of getting started with using control charts?
I think the hardest part is figuring out what it is, what subgroup size you want to use more than anything else. I think that everybody has an idea of what that value is that you're looking for, whether it's a weight, whether it's time, but figuring out that subgroup size, that to me is always the challenge. And that's why I always want to start with some type of time series plot to see what the variation is over time. So then I can figure out what the subgroup size should be and how often I should pull it.
And should you start control charting even if you don't know what your reaction plan should be if you go out of control?
Sure. Gotta see what's going on. I say that because there's always some kind of, people already know how to react to certain things. It's just a question of when do you react? If you can prevent the reaction from taking place. Like I had the control chart in there that I talked about with chemical manufacturing and preventing explosions. If they know that's how they got to react, but if they can react before it explodes, they're in great shape. They can just keep going. When I was making film, believe it or not, years ago, we used to put a lot of stuff on film, and I worked for a place called Eastman Kodak. And making film was a very challenging job because you did it completely in the dark. And you had rolls that were 56 inches wide of the base. You put emulsion on it, which then created the sensitivity for it to become film. And the rolls could be anywhere from 1,000 feet to 6,000 feet long, and all done in the dark. But you had to take samples and you had to measure it. But it was destructive testing because once you expose that film to light, it's exposed. You can't use it. So, a lot of individual control charts were used there simply because of the nature of the way they could test the film.
Awesome. Well, it doesn't look like we have any other questions. That was really great. We do have a session 3 and a session 4 coming up. And the recordings are all posted on our YouTube channel. If you missed a part and need to review it, you can watch the recording at your leisure. And I think we'll end the webinar for today. Thanks, Jim.
Well, thank you, Jenny. And the next one, we're going to be talking about attribute control charts. So these are the charts that are yes, no, pass, fail, why they'd use them, and give you plenty of different examples on how to use them. So great. Thank you.
Yep. And the next one will be 2 weeks from today. Same time, same place. Thanks. Bye.
Thank you. Bye now.